I had made some mistakes during the discussion of RS notation in the previous video, so I want to repeat the study of RS configuration once again. The carbon atom to which 4 different groups are connected. This carbon, where X, Y, Z and A are 4 different groups. Such a carbon is called asymmetric carbon or chiral carbon. Now consider the molecular model of an asymmetric compound where the 4 groups are different. Now here, as I have told you earlier, this yellow ball represents chlorine, which is yellowish green in color, and the green ball represents chlorine, which is greenish blue in color, and this red ball represents bromine molecule, and here it is bromine blue. So the red color is due to, we can say, the reddish brown color of bromine, and the blue color, that is iodine group, and iodine has violet color. So this is bromine, iodine, chlorine and chlorine. Now take another model of the same molecule. You have bromine, chlorine, and iodine. Now I am going to superimpose one molecule over the other. Let us see what happens. When these molecules are superimposed, do you find iodine and iodine coincide, or one iodine comes over the other iodine, one chlorine comes over the other chlorine, then one bromine comes over the other bromine, and one fluorine comes over the other fluorine. So all the like atoms or groups coincide. Hence, this molecule is not an isomer of the other molecule, but these two are the same molecule because they have the same configuration. Now, suppose I am interchanging a pair of groups. So, two groups are interchanged. You can select any two groups for interchange, and here I am interchanging, say, bromine and fluorine. So instead of bromine here, you connect fluorine. So bromine and fluorine are interchanged. So this is one interchange. A pair of groups are interchanged. Now let us see what is the relation of this configuration to the original configuration. You superimpose this molecule over the other. See, chlorine comes over chlorine, and iodine and iodine coincide. Iodine comes over iodine, but fluorine and bromine comes over each other, and here also fluorine and bromine comes over each other. So these two are not the same configurations, but if you place a mirror between these configurations, placed like this. So chlorine and chlorine comes together when a mirror is placed here. So there is equal distance of the bromine groups from the mirror, there is equal distance of iodine groups from the mirror, and this bromine is far away, so this bromine is also far away from the mirror, and again there is equal distance from the mirror to the fluorine and from the mirror to the other fluorine. So we find these two are related as object and image structures. Hence, the first interchange, one interchange can create opposite configurations, or we say during one interchange the configuration is inverted. If this is having, say, R configuration, this will be having S configuration. See, we will see later how to find the configuration. Now this is the original molecule. I am going to make two interchanges, a second interchange here. So a total of two interchanges. You can select any pair of group. Suppose I am changing the positions of chlorine and iodine. Then let us examine both these structures. Here, when you superimpose the new structure over the original structure, original configuration, you find that fluorine, this is fluorine, comes below this fluorine, and this iodine comes below this iodine, this chlorine comes below that chlorine, and bromine comes below bromine. So all the groups coincide with each other, so that these two configurations are superimposable, and if they are superimposable, then their configurations will be the same. That means two interchanges create the same configuration. So one interchange, we say, inverts the configuration. Two interchanges retain the original configuration. So during one interchange, inversion of configuration is obtained. If it is R, then the other one is S. Then two interchanges create the original configuration, so that is retention of configuration, we say. So generally we can say one is an odd number. So odd number of interchanges creates opposite configurations, and even number of interchanges, 2 is an even number, so even number of interchanges create the original configuration. That is the general case. Now, before naming compounds based on their property in a molecule, in an asymmetric molecule, based on RS notation, we have to assign priority of groups around the asymmetric carbon. So priority of these groups around asymmetric carbon has to be assigned for denoting them by RS notation. Now, for assigning a priority to the groups, we select those atoms of the group which are directly bonded to the chiral or asymmetric carbon. And if the atom directly bonded to the asymmetric carbon has a higher atomic number or atomic mass, then we can say it possesses a higher priority. So priority is decided by the atomic mass of the atom directly bonded to the chiral or asymmetric carbon. So higher the atomic number or atomic mass, higher is the priority of the group. Now suppose if two atoms with the two groups with the same atom are bonded to the asymmetric carbon, then the priority is decided by the next atom bonded to the first atom. Now in the case of isotopes binding to the asymmetric or chiral carbon, the isotope with a higher mass number is given preference or the isotope with lower mass number. So for example, if groups D deuterium, that is symbol D, and hydrogen are connected to the asymmetric carbon, then deuterium is given higher preference over hydrogen. So priority of deuterium is higher than that of hydrogen. As I told you earlier, if two groups are bonded to the asymmetric carbon by the same atom, then the next atom decides the priority of the group. If the next atom is of higher atomic number or atomic mass, then it has the higher priority. For example, in the case of methyl group and ethyl group, the atom directly bonded to the asymmetric carbon should be carbon. Then they are the same. So the next atom, that is carbon connected here to this carbon, whereas carbon here connected to hydrogen. So the next atom here is carbon, just a higher atomic number or atomic mass than hydrogen. So higher preference to ethyl than methyl. Then multiple bonds are duplicated or triplicated. For example, C double bond A, we split the double bond into single bonds. So C single bond and single bond. Now both these single bonds are connected to A. So you connect A here and A here. Again, from the part of A, split the double bond into single bonds, and then A is connected to carbon by double bond. So splitting it into two single bonds. A is connected to carbon by a single bond, A is connected to carbon by a single bond. So this is the split pattern, so that here the third atom comes to be carbon. Now C triple bond N can be split or triplicated. Now carbon triple bond is converted to single bonds. Here the valence is shown here. Single bonds, 3 single bonds. Now each single bond is connected to nitrogen. Now from the part of nitrogen there are 3 single bonds. So 3 single bonds around nitrogen. Now each single bond is connected to carbon, one carbon, and one carbon. So this is the split pattern. See, from this example we can split C double bond O, the carbonyl group, into C. This double bond is split into 2 single bonds. Each single bond is connected to O. From the part of O, this double bond is split into 2 single bonds. Each single bond is connected to carbon, so O connected to carbon and O connected to carbon. Now the phenyl ring, phenyl group can also be split in the same manner. This carbon possessing the valency split into 2 carbons, split into 2 bonds connected to carbons. So 2 carbons are connected here, and this carbon again split into 2 bonds connected to one carbon and the other carbon here, and again this carbon is connected by a single bond to this carbon. There again duplication creates such case. So multiple bond is duplicated or triplicated, so that its priority may be increased. Now some groups are given here in the decreasing order of priority. Now OH with oxygen atom as the linking atom with a higher atomic number or atomic mass, the nitrogen with a lower atomic mass. So OH group is having a higher priority over NH2 group, and COOH and CHO. COOH group is C double bond OH, CHO group is C double bond OH. Now both have CO group in common, so we have to find the next atom for disassigning priority to the group, and here the next atom is oxygen with a higher atomic number or atomic mass, whereas here it is hydrogen with a lower atomic number or atomic mass, so that this group COH group gets priority over CHO. Then comes phenyl, then this is called ethynyl group, ETHYNYL, ethynyl group. This is tertiary butyl group, cyclohexyl group, this is vinyl group, isopropyl group, and the vinyl group on duplication we get 3 carbons in a chain. Here this group is common grouping for these methyl groups, so that the second atom is carbon in both cases and the third atom is hydrogen, whereas in duplication of vinyl group the third atom comes to be a carbon. So vinyl group has higher preference over priority over the isopropyl group. Then benzyl, neopentyl group, allyl group, n-pentyl, ethyl, methyl, deuterium and hydrogen. So it's better you study this order by heart. Now coming to the method of finding the configuration of molecules. Now for finding out the configuration of a molecule, we have to convert the formula given into Fischer formula. From Fischer formula we can find out RS notation or RS configuration of the molecule. Now one thing, the most important thing is that in Fischer formula, here we have the Fischer formula connected to the groups L, M, N and O by the asymmetric carbon, and the preference is L greater than, M greater than, N greater than O. We should arrange the Fischer formula in such a way that the group of least priority should be at the bottom of the vertical line. So the group of least priority, that is O, should be at the bottom of the vertical line. You can make interchanges of groups, and you have seen that one interchange inverts the configuration, means the configuration is changed from R to S or S to R. Now an odd number of interchanges will invert the configuration, and an even number of interchanges will retain the configuration. So the group of least preference should come at the bottom of the vertical line. Why this is so? Before that, we shall discuss the R and S notations, how to say that a molecule is having R configuration and a molecule is having S configuration. Now here the priority of L is 1, it has the highest priority. Priority of M is 2, and priority of N is 3, and priority of O is 4. Now these groups are arranged in the decreasing order of priority in the clockwise direction, so that it is R. Now if the groups are arranged in the anti-clockwise direction, then the groups are arranged in the anti-clockwise direction, with the group of least priority coming at the bottom of the vertical line, then we can say the configuration is yes. Suppose the priority of group is like this: L less than M less than N less than O, and the configuration is in the Fischer form. The group of least priority coming here L, then the maximum priority, that is O, then N and M, and here maximum priority is 1 for O, then comes N, second priority number 2, then comes M, priority number 3, and L, the least priority. Then the arrangement of groups 1, 2, 3, 4 in the anti-clockwise direction, so that this is yes. Now by looking at the molecular model, we can say that whether the configuration is R or S. Now you hold the model such that the group of least priority, that is fluorine, faces away from the observer. See, I am holding fluorine here. You can see fluorine. It is having the least priority and is kept away from the observer, kept away from me. Then look at the other three groups. Here this is iodine, this is chlorine, and this is bromine. Now you slightly rotate it. Then you give preference 1 to iodine, which is having the highest atomic number or atomic mass. Then give a second preference to bromine, which is having the second most highest atomic number or atomic weight. Then the third most atomic weight is for chlorine, and fluorine is having the least atomic weight, which is kept away from the observer. Now the order is 1, 2, 3, and the direction is clockwise, so that we say this configuration is R. So once again, you keep the group of least priority away from the observer, and look at the other three groups which are facing towards the observer. These groups are facing towards the observer. So look at the order in which the priority of groups are arranged. Then suppose we draw the Fischer formula of this configuration. This is R. Then on the vertical line, we should write those groups which are away from the observer. See here, you will find that fluorine and bromine, the red ball and the yellow ball, are away from me. So they are drawn on the vertical line with the bromine at the upper end and fluorine at the lower end. Then on the horizontal line, that is the plane on which the groups are directly facing you. The groups are directed towards you on the horizontal plane. They are iodine, which is blue, which is on the left hand side, and the chlorine, which is green, on the right hand side. So I am going to write the Fischer formula here. So on the vertical line below, write chlorine and red ball represent bromine. And on the horizontal line on the left hand side, you write iodine, and on the right hand side we write chlorine. And iodine is given preference number 1, bromine 2, chlorine 3, and chlorine 4. Then it is R. So why insist that the group of least priority should come at the bottom of the vertical line? Why it is? Because we are holding the molecule model in such a way that the group of least priority is away from us. That means the group of least priority will come at the bottom of the vertical line. Only then we assign the priority order to the groups, and then we find whether the arrangement is in the clockwise or anti-clockwise direction. Now I am going to interchange a pair of groups, say chlorine and bromine. So you replace chlorine and bromine like this. Now this is R. So we should get the S configuration. Now again you hold the molecule such that the group of least priority is away from the observer, away from me. Then the order is iodine 1, bromine 2, and chlorine 3. Now the arrangement of groups is in the anti-clockwise direction, so the configuration is S. So we find that one interchange will invert the configuration, means R is converted to S, and you make two interchanges. Say for example, here I am interchanging chlorine and iodine. Then you hold the group of least preference away from the observer. So group of least preference is held away from the observer. Then you find the arrangement of groups and their priority order. Iodine, which is blue ball, is given preference number 1. Then bromine, red, preference 2, and chlorine 3. So 1, 2, 3, that is clockwise, it is R configuration. So two interchanges produce the original configuration. Generally, we can attempt a third interchange. So 3 is an even number or odd number. It is an odd number, so that we should invert the configuration. We should get an inverted configuration. So interchange any pair of groups, say bromine and chlorine. This one was R, and if you are interchanging again, that is the third interchange, we should get an inverted configuration, that is S. Now hold the group of least preference like this. then 1 that is iodine, 2 bromine, 3 chloride. So this is in the anti-clockwise manner, so the configuration is S. So 3 interchanges invert the configuration. Originally it was R, it became S. So we say odd number of interchanges invert the configuration. If the initial configuration is R, then after odd number of interchanges we get S configuration. The original configuration is S. After odd number of interchanges we get the R configuration. And again, if the original configuration is R, after even number of interchanges we get the same configuration. So 2, 4, 6, etc. interchanges. If the original configuration is R, then we get R as the final configuration, and so on. Now the most important thing is that the group of least priority should come at the lower end of the vertical line. That you should not forget. The group of least priority should come at the bottom of the vertical line. Now here one example is given. That is OH, CHO, COH and CH3. Here oxygen atom, since it has the highest atomic mass or atomic number among those atoms directly bonded to the chiral carbon here, OH group gets preference 1. Then CO group is common to CHO and COH, so the next atom, that is hydrogen here and here oxygen, so this group is given preference 2 and this one given preference 3, and the least preference is given to CH3, which comes at the bottom of the vertical line. Then this is not an order, so 1, 3, 2, we have to change it into 1, 2, 3. For that we have to interchange 2 and 3 groups. So COH comes here and CHO comes here. Then the arrangement is in a clockwise manner, 1, 2, 3. So this is R, and since there is only one interchange, the configuration is inverted, means the original configuration is the inverse of this one, that is S. Now here the second example is given. I shall write it once again. You have to assign priority to the groups. Evidently, OH group gets number 1 because oxygen atom has higher atomic mass or atomic number than the carbon atoms to which the other groups are joined. Now it is having a second priority, that is phenyl group has the second priority because it contains a larger number of carbon atoms compared to the other 3 groups. And here, since this C triple bond is being triplicated, greater number of carbon atoms in this structure, so it is given 3 and this is given 4. The thing is that the group of least priority should come below the vertical line. So first of all, you have to interchange say 1 and 4. So during that interchange, we get OH here, that is preference 1, then CH double bond CH2, so interchange number 1, then phenyl is there, so this is 4, phenyl with the preference number 2, and then C triple bond CH with the preference number 3. You can make these two interchanges, then 2 comes here and 3 comes here, so a second interchange, so interchange number 2, interchanging these two, you have C triple bond CH here, that is preference 3, phenyl coming here, that is preference 2, and OH coming here, preference 1, and the CH double bond CH2 coming here, preference 4. So the order is clockwise, so this is R, and since the number of interchanges is an even number, this is also R. So we can assign the configurations by taking the Fischer formula, and Fischer formula can be obtained from the wedge formula easily. Suppose the wedge formula is given like this. Say CS2, CS3, then two broken wedge H here, then BR here, and CS3 here. Now from looking in this direction, the observer is standing here and these groups are directed towards him. So those groups are directed towards the observer in a horizontal plane, should be written along the horizontal line. Right Brahmin, here Brahmin is on his left hand side, so Brahmin here, and methyl is on his right hand side, so methyl here, and the CS2 CS3 is at the top, and the group connected using a broken wedge is written at the bottom of the vertical line. Here preference 1 is given to Brahmin. Of course CS2 CS3 gets preference 2, and this is 3 and this is 4, so it is clockwise and R. So wedge formula can be converted to Fischer. This is wedge notation, this is Fischer